Okay, so thanks very much. Radu and Yura for the invitation. It's my first time in Vienna, and very happy to be around. And this talk is joint work with Ivan Keo, who is a senior arts researcher in my lab, and a joint PhD student, Nathan Buskovic. So the main topic of the talk would be the interface of optimization, and there's problems. So it interpolates somehow between the talk of Mark and the talk of Russell, and also in machine learning. That's the main deep inverse prior, which is I'm gonna try to demystify. Okay, so first of all, what is an inverse problem? We have an object, let's call it x bar, which lives in some finite dimensional vector space. Here I'm gonna assume it's Rn. And we don't have an access directly to x bar. What we have access to is some observations y through indirect measurements with the forward operator f, and possibly with noise, epsilon. This is what we call the form model in inverse problems. And typically, this is, in tomography, this is something that Russell has been talking about too. And what we want to do is to recover the object x bar, or some approximation of x bar, based solely on the knowledge of y and f. Okay? And typically, what happens in practice is that we have much lower number of measurements, let's say m than n, or even if you have the same number of measurements, typically the operator, which is here, is very ill conditioned. And this is the reason we call this an ill-posed inverse problem. Okay, so, sorry. The typical approach that has been developed for a very long time in this community of inverse problems is to use variational formulations to solve this inverse problem. So this is what we call the model-based. Why? Because typically what we're going to do is we're going to minimize with respect to s in Rn, a composite function, which is the sum of two terms. The first term, which is the data fidelity. What this term tells you, basically, it has to be faithful to the forward model, because basically we have the physics of formation of the objects of the observation y from the object x bar, and we want to put this as some sort of information in our model. So we call this a data fidelity term. So here the Ly is some loss. And then you can impose some prior knowledge that you have on x bar. Okay? So if you know that it's sparse, like Russell was doing, you're going to put a function here. Ri tells you, oh, we are sparse. Typically, it could be the zero pseudo norm or the L1 norm, whatever you want. It could be the integer function of the corresponding balls as well. And if you have possibility, you can put the integer function of the positive orthant, et cetera, et cetera. And I'm going to sum all this into this term that I'm going to call a regularizer somehow. And this is a model knowledge, which basically tries to capture some low complexity or some low dimensionality of object you're looking for. Okay, so typically what people have been doing for a long time before moving to deep learning or machine learning approaches, they have been doing a lot of things like Tikhonov regularization, and then sparsity type priors, either with what we call the synthesis sparsity or the analysis sparsity as well, group sparsity to structure this sparsity, analysis sparsity like total variation and so on, and also low rank priors, typically that it can be a very useful in the case of hyperspectral imaging, for instance. Okay, what do we know so far about this kind of models? So the pros is they are very well understood. We have a wealth of theoretical guarantees. We have whole books on this. In terms of recovery, you know exactly under which situation you can have exact recovery, stability to noise, you have algorithms, and you have also some explainability, interpretability of the results, et cetera, et cetera. The cons is that you have to choose your prior. And this is not always easy. So this depends on prior knowledge you have, or as you are an expert, you can impose this by saying, okay, I'm looking for this type of object. And we have a diversity, and so the complexity of object to recover makes this even more complicated. Okay, so then people have started moving in the last 10 years or so to database approaches. So here, the idea is quite simple, is to put somehow a neural network. At the output here, you have the observation, and you let the neural network, so basically this will be a sort of universal approximator of your object x bar. And I'm going to call the neural network G, and the G has an input Y, and it's going to be parameterized by parameters theta, which are basically the weights and biases. Okay. And you're going to minimize with respect to the weights, typically here, theta, this kind of losses or risks. So this is an empirical risk, and we have a loss here. And we're going to measure the difference between what is output from the neural network and the xi's. And you have pairs, yi, xi, that you know precisely. So it's a sort of supervised, so it is a supervised approach, but here you have sort of labeled data. For each output, you know exactly what is the original object xi. So if you minimize this, what people in machine learning call training, you hope to be able to train the network G here, and especially the weights here, insert that in a way that if now you have a new observation, you're going to have something which is close to the underlying objects. So this is what you're hoping for. And this is the reason we call this a data-based approach, because we need some training set. Okay. So the pros is that you can, this is what people have been doing for some time now, is they can use off-the-shelf neural network learning frameworks. They think that there is no model to think about. I think it's not quite so, because you trade something for something, so no free lunch. And you train this once for all, in such a way that once you train, you can infer the new object based on the new observation. In fact, this is supervised, meaning that you must have a lot of training data, okay? And of course, when you think that basically you have no model, actually you do have a model, because you traded the prior knowledge, the prior design that you have in the variation models, okay, in the neural network design. Okay, what is the architecture I have to put here for my approach to perform well, okay? And the second problem is that you have lost completely the physics. We know that y comes from x through f, and we have some noise. There is no f whatsoever here, okay? You have lost all the physics of the formation of the object. And of course, because of all this, we have a lack of guarantees from the inverse problem perspective, okay? Recovery, stability, explainability, everything we had in variation models, we don't have them anymore here. Okay, what can we do? We can move to some sort of hybrid approach, trying to hybridize, variational models and the data-based approach. So to mix them, what we're going to do is basically we can, for instance, learn the regularizer. Okay, we have a variation model, and then we learn the regularizer. You can see this as bilevel programming. You can see it also as an optimal control problem, different point of views. And either you learn the regularizer either explicitly, the function itself, okay, or you can learn it in some implicit way, okay. So for instance, you can learn the projector, the proximal operator, okay. So these are what people are now calling plug-and-play approaches. And also what you can do is, okay, I have my variational problem in the first approach. I'm going to cook up some algorithm. This algorithm will be, let's say, a discrete with continuous time dynamical system. I'm going to control it. And this is what people call enrolling approaches. They're going to learn all the nonlinear parts in the algorithm, for instance, if you have some procs or whatever, and try to learn this from some data, et cetera, et cetera. We have many different approaches. Okay, again, so basically, the approach is, or at least the motivation is to get the best of both worlds, and to account at least for the forward model, because here now you can take into account the fact that the image or the object that you are observing is not something that comes from nowhere, okay? And you're gonna learn explicitly or implicitly the prior, and you train once for all, and you can have some guarantees, but not from the inverse problem perspective, because it's quite complicated. But basically what people try to prove here is that their learning procedure will converge somehow, and typically you're going to learn some non-expansive operator or some co-coercive operator, control the Lipschitz constants, et cetera, et cetera. Okay, the cons. Of course, it is again supervised. You must have availability of training data. First, you have to design the neural network, and even in this type of approaches, for the enrolling and other type of approaches, you have even many neural networks, not only one, okay? And from the inverse problem perspective, again, the recovery, stability, explainability, you don't have really a guarantee. This is a completely open problem, as far as I know. Okay, so I'm not going to move directly into this very complicated problem. I'm going to simplify it a little bit, even a lot. So what I'm going to do is the following. I'm going to be interested in this kind of approaches that we call the deep inverse prior. And why this name? I'm going to take y here, okay? And indeed, I'm going to use a neural network to synthesize somehow the object that will approximate my original one, x bar. Okay? And then I'm going to say that the output of this neural network, I'm going to compare it to y once I put the output of the network in the forward model. Okay? Just think about it, y minus f evaluated at the output of the neural network. Okay? And now I'm going to try to minimize the weights of the neural network here in order, for instance, that this somehow risk is minimized. And actually, what I'm saying here is I'm putting some prior. I'm saying that my x bar itself stems from this set here, which is the set of, let's say, objects, x, gu, theta here for u fixed, where theta is among all possible weights in some, let's say, non-empty set, possibly bounded. Okay? And typically what I'm hoping for is that there is some theta in such a way that x theta will be close to x bar. This is the hope that we have. Of course, the minimization here, which allows for a lot of different signals, and the problem is very non-convex. You don't have any clue that this will be actually learning something which is close to x bar or not. Okay? But what we're going to see is what's important is not the minimization problem. And this is one of the main messages I want to convey here. What makes basically machine learning works is not the minimization problem. It's the dynamics of the optimization algorithm. So, and you have to mix both. The dynamics is very important because the dynamics will bias your solution to some typical solution, which is close to the one that you're looking for somehow. And this dynamics will introduce somehow an implicit regularization. This is really the main message to keep in mind. Okay, this is an unsupervised approach, of course. I don't have any training data here, but of course, and the input is some generator, let's call it U, which is distributed according to some measure mu, and what we're going to use also is an implicit, an early stopping strategy in order to cope with the noise, for instance. Okay, just when I saw this the first time, yeah, of course. Yeah, okay, excellent question. Okay, so what people have been doing is to draw the U from a very simple distribution to sample from, uniform, whatever, okay? And so far it doesn't have that much influence, but in fact it does. It does because this is basically generative models, okay? And in fact, because of the continuity, so the network, the way it's built, it's continuous, okay? So if the object that you have lives in some manifold or has a distribution which is supported on some manifold, then basically this is okay. However, if the support is disconnected, for instance, then if you draw your U here from, let's say, uniform distribution, it will interpolate between the supports. And this will create what we call hallucinations. So basically, in this case, you would better choose U to be drawn itself from a mixture of disjoint distribution with disjoint supports. So this is a really hot topic in generative models. Yeah. I do, is the why. Why?
No, I'm sorry.
No, I don't have any training. That's a, I'm assuming I don't have any training because this would, we can mix both, but this.
Your information.
No, okay, this is a different philosophy. It's an unsupervised way, okay? I only have observation and that's it. And of course, this means that each time you will have to train your network. Not for lunch again. You don't have data to train. Okay, when I saw this the first time, it was really surprising to me that it could work, and it actually works. Okay, so I'm just here putting a simple simulation that my students did, very low dimensional, by the way. So I have a deep learning problem. So I have an image, x bar, which is this guy here. So see if you can see it well. Anyway, and then I blurred this image, and then I added noise. And the observation is this. I'm feeding this to my neural network. I'm minimizing the previous objective. Okay, and looking at the dynamics of gradient descent, I'm just using gradient descent here. So I'm starting with complete noise, and then at this iteration, we start seeing something. Only from this. Okay, and then 1,000 iteration, it somehow didn't move that much, and then we stopped here. Okay, is there something happening there? So I don't come from the machine learning community. I come rather from inverse problems and optimization community. And yeah, go ahead. What's that? Say what? Iteration, you mean? Yeah, you'll see them shortly. Yeah, sure. I am training this with gradient descent, and here it is the iteration of gradient descent. Okay. So, okay. So here you can account for the forward model. It is unsupervised, easy to implement with very good empirical success, as I just showed you. And however, you have to train to optimize for each object to recover, of course. And there is no theoretical guarantee so far. And what we try to do is really to answer this question, why and when it's going to work, okay? So what I'm going to present shortly is more technical, but typically, the main message is we have guarantees either in the observation space, in the space of y, but also in the parameter space, which is the x bar here. So we have convergence to zero loss. We can use early stopping. And there's some assumptions. Typically, your operator has to be invertible somehow, not in the whole space, of course. Then we can have recovery of some good approximation of x bar. And we try to do this in a very general framework with Ly under verifying some global coordinate regularization inequality, hence the link with Mark's talk. And we're going to put forward the role of the desingularizing function in all this. And also, I'm going to show you, so I'm going to have a very dry condition, and I'm going to show you how to verify it in practice. And this is where the role of overparametrization of the neural network comes into play. So basically, you have to design properly the architecture of your neural network for everything to work. Okay. So to make things simpler, I'm going to assume that this guy here is linear for the rest of the talk. Okay. So the first result, okay, is this one. But before this, I'm going to, okay, so I think that you mentioned this before. But typically, I'm going to assume that we have globalized scale inequality. So typically, if I have a convex function, which is summarized right, it's going to be true. But we have much more class of problems for which it is true. But as you know, scale inequality is just a simple inequality that tells you that your function has to be sharp if you reparameterize it, okay? And it is also a local gradient domination condition. This is exactly what you see here. And of course, it is very popular. And in fact, the one which is very popular is the Lyazovich one. Cordical is more complicated, but more general, let's say. Okay, and it is also very closely related to error bounds, to derive complexity bounds from descent algorithms. And I'm giving here some examples like convex function with sufficient growth, uniformly convex functions, real summarized right convex functions. They verify all these inequalities. Okay. Okay, I'm going to talk here about the, the iteration. So I'm going to train my neural network. I'm trying to minimize this guy with respect to the weights theta. I can either use a very simple gradient descent. So this is the continuous form of it as a Cauchy problem. So theta dot equal to minus the grad with respect to theta of my objective here. Or I can discretize it. So in the rest of the talk, I'm going to focus on this, but in the paper, we have the discrete version as well. And I can use also other algorithms. Why using this one? And for instance, I'm going to study another algorithm, which is here an inertial algorithm with some damping, okay, viscous damping here that you have. So this sort of inertial, not accelerated. I don't have any proof of acceleration in the general case, but I'm going to prove that in these contexts, it is faster. And I have also another term here, which is less usual to people if you compare it, for instance, to the heavy ball method. So this is basically another damping that comes from the Hessian, and we call this a geometric-driven damping, hence the acronym here. And if I discretize this properly, I end up with this algorithm that we call inertial gradient with explicit Hessian damping. Okay, so people who are familiar again with the heavy ball method, we don't have this. We only have this. Okay, so in the rest, to make things simpler, the loss will be 0. At its minimal value is 0. It's going to be C1, whose gradient is locally Lipschitz continuous, and I'm going to assume that the loss also is globally KL. Okay, and also the activation. The activation I'm going to use in these guys here, in my neural networks, is going to be assumed to be uniformly bounded with the uniformly Lipschitz continuous derivative. So typically, you take the sigmoid, it's going to be true. Okay, so let me guide you through here. What this theorem tells you is the following. Yeah, sure, I'm almost done. Okay, so I'm going to take this as the smallest non-zero, the first non-zero negative value, which basically will express the conditioning of the operator. And what this theorem tells you is that, it tells you that if you initialize around a non-degenerate point, so what does it mean? Basically, it tells you that the network has to be such a way that the Jacobian is injective. And if these guys here are such that R prime and R are sufficiently small. So in this case, okay, the loss would converge at a rate that depends only on psi, sigma A and sigma min of the Jacobian of the network. And theta t that you have here will converge to a global minimizer of the loss, okay? And of course, by continuity, the signal itself, or x, will converge as well. Okay, and now if you have the loss has unique minimizer, then we know that we're gonna converge to y. So this is the zero loss. It means that basically you're gonna overfit to the noise as well. And in order not to overfit to the noise and avoid this phenomenon, we have to do some early stopping. And this is exactly what is stated here. You have to stop sufficiently early in order not to overfit the noise. Okay. So again, I insist on the fact that here what it tells you is that if you start as at a non-degenerate initialization, basically the trajectory will be close to initialization. This is what it tells you. You're going to be in a ball around your initialization, and this ball is controlled by this parameter R. Okay, so here you have the rates. This is quite usual for people who are used to KL inequalities. So we have sublinear rate. If the desingularizing exponent in the Lorazevich case between 0 and 1/2, you have linear rate for alpha equal to 1/2, and otherwise you have finite termination. Okay, so basically, this is what I was saying. It's going to remain around the ball. But basically, in fact, people who are familiar with dynamical systems will recognize here somehow a consequence of the Hartman-Grobman theorem. So this theorem tells you that the local, if you take an autonomous system, dynamical system dot gradient set, and in fact, if you are in the neighborhood of a hyperbolic equilibrium point, so hyperbolic, it means that it is an equilibrium point, and the Jacobian, okay, of what drives the autonomous system has to be positive damping, okay? So, no, sorry, it has to be non-singular. And this is exactly what it tells you. You know, the Jacobian has to be non-singular. This is exactly what you have here. And this tells you that basically the behavior of the dynamic system will be topologically conjugate to the linearization. And the fact also that the Jacobian that you have at 0 will carry over through the iterates makes a connection with the what we call the conservation laws for dynamical systems and symmetries via the Emmy and Noether theorem, because you can see the gradient flow as an isolated evolving physical system. Okay, in the parameter space, you have to impose an extra condition, this one. So this one is much, much weaker than imposing that your operator A has to be injective. You have to be injective only at the tangent cone of your parameter space taken at your origin vector x bar. Here, if x bar belongs to sigma, x bar will coincide with x bar sigma, but otherwise, if it does not, you have to take the projection of x bar on sigma. And basically, what the bound gives you are three terms. The first term that comes from an error from optimization. The second, approximation. X bar may not belong to sigma, so we have an approximation. And the third one is because of the noise. And as you can see, again, what you have here are the smallest eigenvalues with singular values each time of all the operators that come into play, which is what was expected. So just to show you that if we replace gradient flow with the one that I showed before with the Hessian-driven damping, for instance, we can improve the convergence rate from this to this. You see, again, here we have somehow the conditioning, and here we have only the square root of the conditioning, as we expect. Okay, and now how to provide all these conditions? You have to overparameterize. So how to overparameterize? I'm going to take a very simple example, one with one hidden layer. I'm going to initialize here with random initializations from appropriately chosen distributions. And the message is this one. The number of nodes that you have in your neural network has to grow this way with respect to the dimension of your signal, and also of the dimension of the number of observations. And this is with high probability, and typically it's going to behave like k greater than some constant times n squared. Okay, so to conclude, we have verified all this numerically. Turns out that it works, and which basically showed us that we were not that far from the right track. And this is the result I showed you before. Okay, just to conclude, we have some guarantees on inverse problems trained with for neural networks. What's important, again, I insist on that, it's not a minimization problem, it's the dynamics. And we're working on the non-smooth setting, so discrete setting, it's already done, it's on the paper. And the stochastic setting, because a lot of people use, although here we don't need it because we only have one observation. So a GD is not really devised, but still we can do some analysis in the stochastic setting if you want. We want to move to other NN-based frameworks, supervising setting, physics-informed neural networks, et cetera, and also to investigate other overparameterization regions. So I'm done. Thanks very much. And the papers are on my page.